Now I'm pleased to welcome today's speaker, Dr. Lisa Dang.
All right, hi everyone. So let me just try to show my screen. Excellent. It's a little offset. All right, here we go. So hi everyone, thank you for being here. For some of you, it is the evening in the Eastern time zone, so I appreciate that you're taking time out of your evening to be here. And I'm honored to be able to talk about observing climates of distant worlds with infrared space telescope. So my name is Lisa Dang. I recently just graduated from McGill University, and then I am going to move around in the same city, just going on the other side of the mountain, where I'll be joining Université de Montréal as a postdoctoral fellow. So today, I wanted to hopefully convince you by the end of my talk that right now is a really good time to be an infrared astronomer. So to begin with this, I just wanted to take a couple of steps back and give you a little bit of context for what studying exoplanets is and what these distant worlds are. So for a long time, the solar system planets has long been the primary inspiration for understanding how planets form and how they evolved, but also how their climates have shaped their environment or are shaped by their environment. And so it was then theorized that all planets started as a rocky core located at the orbit or following the orbit that they reside on today. And the core is farther from the sun, where it gets cold enough for abundant volatiles to condense. We're able to accrete large envelopes and then form these large gas giants that we know today. So Jupiter, Saturn, Uranus, and Neptune. Meanwhile, the high temperature of the inner solar system caused volatiles to be very scarce. And so that consequently limited their ability of these planetary cores to accrete large envelopes of gas. And so instead of having these large gas giants, you got these small terrestrial rocky planets like Venus, Earth, Mars, and Mercury. So this, however, changed in 1995. So in 1995, there was the first discovery of the first hot Jupiters, and this is still one of the most astonishing discoveries or planetary discoveries up to date. So the discovery was a Jupiter-sized planet residing on an orbit that is well within that of Mercury, where we didn't think that these planets could possibly form. And so in parallel, there was also another increasing number of solar system investigations that suggested that the solar system history was also a little bit more dramatic than we previously thought. And so this forced a bunch of scientists to kind of revisit our understanding of how planets form and how they evolved, giving rise to a lot of planetary migration theories. And so even though our solar system doesn't have any of these hot Jupiters, they're still one of the best studied exoplanets, and I'll talk a bit about this later. And one of the reasons for this is that they're the easiest planet to observe. And so this is why this particular type of planets were also first discovered. So the discovery of 51 Peg-B, which is the first hot Jupiter that was discovered, is what I like to call a trailblazing discovery because it opened the doors to a bunch of new fields. So quickly after the discovery of the first exoplanet or the first hot Jupiter, planetary scientists were in search of pathways in which you could create such a planet that formed on its orbit. Some climate scientists were making models to predict what kind of atmosphere you would expect on these planets that were very extreme because these planets were very close to their host star. And then also thinking of what possible physical properties could govern the climate of these planets. And then on the other side, a bunch of astronomers and astrophysicists started thinking about new methods on how we can discover them, how we can design exoplanet hunting surveys, and develop modern technological advances that would push boundaries of how or like what kind of planets we would be able to detect. And so this is just a few examples of the entire field. And because of that, it was awarded the 2019 Physics Nobel Prize a couple of years ago. So as of today, there are now 5,000 confirmed exoplanets in almost 4,000 different exoplanetary systems, implying that some of these stars have multiple exoplanets, just like the solar system. And so far, only shy of just below 200 terrestrial planets, which seems like a small fraction, but that's actually because they're very challenging to find. And I'll talk a little bit about this a little further. And so Now we know of thousands of exoplanets, and this is largely due to the success of exoplanet hunting missions, such as the Kepler missions. And what's really impressive is that some of these really successful missions cost even less than a Marvel movie. And so here, what I'm showing is a figure of the demographics of all known planets that we know today. So the x-axis of this is a semi-metric axis of the orbit of the planet, and the y-axis is where you have the mass of the planet. So you can see all of these planets represented in the back, and they're color-coded by their detection methods. So you can see that the majority of the exoplanets found to date are vastly different than the ones of the solar system. So even though it is unlikely that we will ever get the same level of details about these distant worlds than we do about the solar system planets and other bodies, the large diversity of exoplanet actually provides us thousands of study cases to sort of refine origin theories about how their climates are shaped by their environment, and etc. And so if you naively look at this plot, you would think that nature is not really good at making planets like the solar system. However, the exoplanets here are color-coded by their different detection methods, and they probe different parameter space. But at the moment, the reason why we can't find the ones like the solar system is just because of the limitation of our current instruments. So in fact, detecting an exoplanet directly is really hard. So getting a direct image of an exoplanet, as shown on this GIF here, so you can see like in the middle, there's supposed to be a star, and you see all of these like 4 little blobs that are orbiting around the star. It's actually very difficult. So just to give you a comparison of how difficult it is as difficult as photographing a fly that is flying next to a lighthouse beam that is standing about 6 kilometers away from you. So a direct image of an exoplanet in the vicinity of a bright host star is really tricky because first, the planetary brightness is sort of drowned by the massive radiation that is emitted by the host star because they're dimmer. But you also need a very high resolution, a high spatial resolution, in order to make sure that the planet and the star don't fall in the same pixel, which is something that happens a lot. So as a result, most exoplanets discovered today are not via, most exoplanets discovered via direct imagings have large separation from their host star, and they're also super large, at least large enough to emit or reflect a bunch of flux from their host star or themselves. So even then, we often have to suppress the light coming from the star. So we have to do this like fancy process where we suppress the flux from the star in order to reveal or improve the contrast between the planet and the star. So the resolution of these images also, these are extremely high resolution, so you need very large telescope. But even though it's really hard to detect these exoplanets directly, remarkable advances have enabled the detection of a bunch of astrometric and Doppler exoplanets by leveraging their gravitational effects on their host star. So conservation of momentum requires that a planet and a host star also orbit their common center of mass. And so as the planet is orbiting around the host star is also sort of orbiting slightly or having its position change slightly as it's orbiting around their common center of mass. And so if you have what we call a face-on orbit, you will be able to detect these movements or these periodic movement of the star instead of the periodic movement of the planet. And so even though we're not seeing the planet here, if you have really precise centrating positions or centrating on your images, you can start constraining properties of the planet that is orbiting around it. So this is one way of doing this. And this also gives you insights about how massive this outer planet is compared to the host star. In fact, astrometry is a very, very old detection methods because this is one of the ways that we detected the planets of the solar system. So we used to look at the sky and look at all of these stars and measure their position very precisely. And then we discovered that the planets of the solar system looked like stars, but they were not moving in the right direction. So another way of leveraging the same phenomenon is Doppler planets. So using the same concept of conservation of momentum, but now using a different methods of detection. So Doppler planets, instead of residing on these face-on orbits, they are on these edge-on orbits. So what we are going to observe is the radial flex motion of their host star, which can be detected in spectroscopy. So if you have spectroscopy time series, so observing spectroscopically over time, you can start measuring the radial velocity of this star as the spectral lines of the star is being blue shifted and red shifted periodically. So yeah, so for both astrometric and Doppler planets, the observations also give us information about the mass of the planet that is orbiting around, but instead of finding the planet directly, you're looking at the effect that it has on the star. So one important aspect that we don't get, so we get some properties or some constraint on the mass of the planet, also on the size and the shape of the orbit of the planet, but the information that we do not get is how large the planet is. So we can know how massive it is, not exactly knowing what kind of density it has. So another way of detecting these exoplanets is by detecting the gravitational effect of the entire system. So now we're not interested in the effect of the planet on the star, but the entire system on their neighboring environment. So these planets are referred to microlensing exoplanets. So, oh no, I'm missing a slide. Okay, anyways. So basically the slide that is missing was a little video showing you what gravitational lensing is. So for those of you who are not familiar with gravitational lensing, when you have a mass that is large enough, it can make some perturbation in space-time, which bends space-time, and therefore your body of mass in the middle that we will call a lens will be able to deflect the lights or the neighboring rays of lights that is passing nearby. And so if you are an observer, on Earth at the bottom here, and you're observing a far away source of light, as the lens in the middle is passing between you and the source behind, it will magnify the source behind, and suddenly as an observer, you will observe an increase in the brightness of this source behind. And so this phenomenon here is called gravitational lensing and was predicted by Einstein back in the 1930s. And so now, if you were to get a microlensing event, you would see here the little curve that is in gray here. So basically, this is the flux over time. So you see an increase in the brightness of the source, and you see a decrease back to the normal brightness. However, if this lens were accompanied by a less massive companion, such as a planet, so if you had a planet and a star in a planet system, what would happen then is that this planet can also perturb the light or the trajectory of the light that is nearby and further perturb this lensing. And so what we would see is not necessarily, so what we're going to see is not the planet, but how it's going to manifest itself is by a little perturbation here in the light curve. And so this is by comparing what you would call a curve that you would get from a single lens versus a curve that you would get from binary lens. So finding microlensing planets from the ground is extremely hard, but one of the big advantages of microlensing is that you don't need to observe any flux from the lens and from the planet itself in order to infer their presence. And so that allows you to find exoplanets that are very far away. And for some reason that you can ask me if you want to discuss later, it is also mostly sensitive to planet that has large separation from their host star. So unlike the detection methods that I talked about earlier, this one is sensitive to planets that are more analogous to the solar system. And in the near future, we are also going to have the Roman Space Telescope, which is an upcoming mission here that aims to use the advantage and the precision of space-based observatories in order to find hundreds of planets using this particular method. And so you can see here the sort of like dashed line represents basically the limitation curve. So we're going to be able to find planets that are even lower in mass. And then finally, the last method that I want to talk about today, which is by far the most successful of all, is detecting transits of exoplanets. So transits are an intriguingly simple way of finding a planet. So when a planet is on an edge-on orbit and passes in front of their host star, it's going to block incoming flux from the star. And as the planet, and then as a consequence, the planet is going to appear a little bit dimmer. So you'll see a dip in the brightness, as you can see here. In order to make sure that this is not a transient feature, that it's not some kind of random object passing in front of the star, you need to observe it periodically. And so once you find more than 3 transit with the same period, then you can assess that this is a planet that is gravitationally bound around the star. But the culprit here is that you have to observe the planet and the star for the entirety of their orbit. And so this biases you towards close-in planets, so planet with shorter orbits. And so now, once you combine all of these different methods of detection with all their different biases, and if you understand them very clearly, then you can start identifying trends in the type of exoplanet that you're observing and detecting, and sort of where they're laying out. And so patterns in the distributions of known exoplanets can allow for theories, or can allow for testing the theories of origin and evolution for planetary systems. So while the community has become much, much better at finding these planets, there are some of us that have moved away from the detection era to what I'd like to call the characterization era. So like I said earlier, it's really hard to detect a planet directly, but you can still get photons from these exoplanets. And so when you're observing the star, sometimes the planet is also in the same pixel. And so you get both photons from the star and the planet. And the game here is to try to disentangle the two of them. So here I have a plot showing black body emissions from different stars at different temperatures. And so you can see here that blue stars that are much higher in temperature have the peak of their black body at much shorter wavelength. A yellow star or a G star like the sun is going to peak in the visible part of the spectrum, and this is why we see the colors. I think this is why we see the colors that we see. And so for stars that are even colder or not as hot as our stars, like red stars, their black body will peak at infrared light. And so you can imagine that for a hot Jupiter, which is a planet that is really, really hot, that can achieve up to 1800 Kelvin, will have their black body peaking farther in the infrared, even though it's emitting less light. You can see here that if you have a star planet system that is a blue star or a yellow star with a hot Jupiter, then the contrast between the star and the planet is going to be smaller. So basically you're getting more photons from the planet, less photons from the star, which allows you to have a better contrast and maybe be able to observe or detect photons from the planet. So in 2005, thermal emission from a planet's atmosphere was detected by observing the planet being eclipsed by the host star. And so you can see here at the bottom, you have on the right a little like cartoon of a star and a planet orbiting around the star. And then here you see the transit here, which is what happens, the dimming of light when the planet is passing in front of the star. But then as the planet is passing behind the star, you also see this little dimming of light here. And so this is basically removing, or for a moment, you are not seeing any photons from the planet, which can determine how much photons you're seeing from the planet otherwise. So like I said, hot Jupiters are the easiest planet to detect, and therefore they're also the best to be characterized. And so I'll give you a little bit more context about these objects because I talked about them a lot without explaining what they are. And so these are gas giants that are blasted with stellar irradiation. And they are synchronously rotating, resulting in a permanent day side and a permanent night side hemisphere as illustrated here. And so because of the synchronous rotation, we're also expecting drastic temperature gradient between the substellar point and the antistellar point of the planet. So as a planet is transiting around the host star, like I said earlier, you'll see a transit and an eclipse. But also, if you observe the planet in between the transit and the eclipse, you also start to see variation in the brightness that is caused by the planet. And so on the right here, I have an example of an infrared phase curve of a planet called HD 189733b, where you can see the planet's transit in the middle. You see the secondary eclipse at the two ends, but if you zoom in and what's in between, you also see this variation of brightness that is caused by the planet. And so what I'm trying to show here, or what I'm trying to argue here, is that phase curves are extremely rich in information because you don't see the planet's atmosphere only on one side, but you see all sides of the planet's atmosphere as it's orbiting around the host star. So if you notice here, the peak of the phase curve is also not exactly coincidental with the time of secondary eclipse. And this is often indicative of a shift of the hottest region of the planet from the substellar point. So in this case here, you can take this phase curve and do the inverse problem, where you can inverse this into a longitudinal brightness profile and sort of pinpoint where or in which direction winds are blowing, and then moving this hottest spot from the substellar point. So these detections were made using time series observations with the recently retired Spitzer Space Telescope. So this is an infrared observatory located on an Earth-trailing orbit, where the distance between Earth and the observatory is increasing over time. So this is where it launched, and now it's sort of getting much further away. And the reason why it's retiring now is that it is moving so far away now that it's on the other side of the sun, and it makes it really complicated to communicate with it. But the original mission of Spitzer was to observe what can be summarized as observing the old, the cold, and the dusty. So observing distant objects that are very low mass and very faint. However, Spitzer wasn't designed to study exoplanet, but the clever choice of the orbit made it ideal for time series observations, unlike Hubble. So it made a lot of substantial contributions to understanding exoplanets, but it also helped setting the stage for a future mission that I'll talk about later. So, like I said, shortly after the discovery of the first exoplanet, there was a lot of climate scientists that wanted to understand what kind of climate you can end up here. And so what I'm showing here are general circulation models. So basically, these are atmospheric models of planets for a typical hot Jupiters. And so in order to read this, the colors in the back represent the temperature of the planet at different location on the planet. And the arrows that are on top of these plots represent the direction and magnitudes of winds at different locations on the planet. One thing that is very particular about these models is that all of these simulations also predict a strong equatorial super-rotating jet that is causing the planet's hottest region to be shifted from their substellar point to the east. That is represented by the yellow dot. And so the first few published Spitzer phase curve all had, and these are the corresponding thermal maps illustrated here, they all seem to exhibit some kind of eastward offset or an offset that was consistent with 0 as predicted. And this was largely interpreted as evidence for the feature that we saw in these simulations that it showed on the other slide. But in 2016, we stared at a little young exoplanet. So it was a really young hot Jupiter. And then what we found is that the peak of the phase curve didn't occur before secondary eclipse, but rather after. So if you were doing this exercise of converting into a longitudinal brightness profile, in this case, you would have a planet with westward wind. And so now it was the first discovery of an atmosphere that didn't behave like the other ones, which is challenging our understanding of planetary atmosphere a little bit. But other things that the Spitzer Space Telescope was also able to do, it got phase curve of an eccentric planet, and it was able to, so eccentric planets are on eccentric orbit, and therefore their distance to their host star changes on the course of the orbit. And so this leads to what we call eccentric seasons. So they don't happen in the Earth very, very often, but on planets on very high eccentric orbits, that could happen because you have less flux when you're approaching apoapse and more flux as you're approaching the star. That could lead to very strong seasonal variation, as you can see here. And one thing that we didn't expect here, so the bottom gray line is sort of the expected theoretical curve for this phase curve. The Spitzer observation showed that the planet was emitting more flux than it was receiving from the host star. And so in this one, we tried to compare sort of what we were seeing here in the phase curve with other properties of the planet. And we also noticed that the planet is what we call inflated. So planets are expected to have some kind of radius depending on different properties of the planet. But this one was a little bit more inflated. We can talk about it later if you're interested. But essentially, it was giving us hints that there might be tidal heating or nuclear fusion happening in this planet. So this planet happened to be a very massive planet. And because it was lying very close to what we call the deuterium burning limit, it was possible that it was not actually a planet, but rather a failed star or some kind of star or some kind of planet or some kind of between the two, really, that still had deuterium to be burned. But at some point, it was going to run out of this deuterium and sort of cool down into a planet, basically. So it's a star, or it was a beginning of a star that ended up being a planet. And then another benchmark achieved with the Spitzer Space Telescope. So I talked about these large hot Jupiter that are really hot and on weird orbits, but we were also able to observe smaller planets. So these, so the planet that I'm showing here, this is again a phase curve, but you can see that the shape is different. The transit is much bigger, the eclipse is much bigger, and the period is much shorter. And this is actually a very, very short period planet. So it's a planet that I'd like to call a lava whirl. So it's a planet that has composition comparable to that of Earth. But instead of being located on an orbit like the one like Earth, it's located on an orbit that it's so tight that it only takes 1 day for the planet to do a full revolution around their host star. And so what we find here are sort of planets that are a little weird. So the reason why I call them lava planets is because they're rock in composition, but because they're so close to their host star, their day side is molten. And so you have molten magma oceans on the day side, and their atmosphere could be made of evaporated rock from this magma. And so this is just an example of one of the discoveries with Spitzer. But what I wanted to talk about today, so even though exoplanet science was not an initial objective of the Spitzer mission, in the end, it became a substantial part of the mission. And what was really important is that it really helped setting the stage for future infrared observatories like JWST. So the Spitzer Space Telescope retired in January 30th, 2020, but this is because it was being replaced by the mother of infrared space telescope, JWST. So JWST is an ambitious giant infrared space telescope, an mission that was led by NASA with the contribution of the Canadian Space Agency and the European Space Agency. JWST turned out to be one of the most complex space telescopes ever built. It's an infrared space telescope that has to be shielded from thermal radiation. It has a primary mirror that has a diameter of 6.5 meter, which is huge. And it's made of 18 hexagonal pieces of mirror, each coated with a very thin coat of gold, and each individually adjustable as well, giving you this sort of like very iconic honeycomb-shaped surface. So the entire mirror of JWST is about 25 square meter, which is about 6 times that of the Hubble Space Telescope. And one of Canada's contribution to this mission is one of the instrument aboard called NIRISS. So NIRISS is the Near Infrared Imager and Slitless Spectroscopy, spectrograph, and it was designed specifically to detect and characterize the atmosphere of exoplanets. And so I'm just showing you little images of this really awesome telescope. So on the right here, you have the mirror of JWST, so you can compare it with the humans at the bottom for scale. And one of the big challenge with this big telescope is that it had to fit in a rocket. And so you had to fold it, fit it in the rocket. And then finally, after about 20 years or maybe more of wait, it finally launched on Christmas. So on December 25th, just last year. And so this is a little GIF here, a little footage of JWST detaching from the spacecraft from December 25th. And then here it's continuing its long trajectory to L2, one of the Lagrange point of the Earth. So one of the things with JWST is that sending it to space was not the last thing we had to worry about. We had to wait for it to sort of unfold itself. It had over 300 points of failure that had to go perfectly, otherwise the mission would fail. It had to also, once it arrived at its destination, it had to cool down for another 6 months before it could start observing. So luckily for us, all of those went super well. And last month, JWST delivered its first images to the public that some of you may have seen or heard of. So here we have the beautiful Carina Nebula. We have a beautiful Ring Nebula here. And this is by far my favorite image, which is a deep field where you can see these gravitationally lensed galaxy, which is pretty cool. And on this image, we also have some of the very first or some of the oldest galaxies we've ever detected. So some of them are redshift 25. We can talk about what that means later. So people often refer to JWST as the successor of the Hubble Space Telescope because of its spectroscopic capability. But I think Spitzer is the real predecessor of JWST because they both probe infrared wavelengths. And the detection that were made with Spitzer set the stage for JWST. What I mean by this is that everything that Spitzer could observe, we knew that if we pointed JWST at it, we would be able to observe a signal. And so sort of the first few targets that are going to be observed are likely targets that are guaranteed to have signals to be detected. So I talked about the spectroscopic capability of JWST. So why does spectroscopy matter? And the reason for this is that because it's more informative than just getting flux without knowing which wavelength it's coming from. So one way of explaining what exoplanetary spectroscopy or atmospheric characterization with spectroscopy would be like. So here from physics or most courses, you've probably seen this. So when you have a light source that is white light, you will get a spectrum that is looking something like this at the top. If you have some kind of gas cloud that is between you and that light source, then the gas cloud can absorb some of the light coming from the light source depending on its absorption feature. So what you would see is some wavelength where light is missing. On the other hand, if you don't have a light source, so if you're only observing whatever is emitted from the gas cloud, you will also see this emission line here. Rather than seeing the whole spectrum, you're only seeing what the gas cloud is emitting. So now I've talked about absorption and emission, and we'll see them again in the next couple of slides. So among the wonderful images released in July, there was also a transit of an exoplanet that was released to the public. So this is a spectroscopic transit, to be precise. In a way, it means that we got a transit like what we see in the left here at all different wavelengths. So for each of the points that you see on the plot on the right here, we got a transit. But the transit depth that was measured at these different wavelengths was not the same. And this is why you see all of these wiggles and bumps in the spectrum here. So on this side is what you get when you get a spectrum of the planet. So you're getting a bunch of transit at different wavelengths. And then depending on what wavelength you're looking at, the opacity of the atmosphere is going to look different. Sometimes it's going to be more opaque, sometimes it's going to be less opaque, depending on the absorption and emission feature, or in this case, depending on the absorption feature of the atmosphere. And so what we end up with here is a spectrum like you see on the right. And these little bumps here that we can identify by eye are water features. So basically this is indicating that this planet, WASP 96b, has some water in the atmosphere. But it's going to take a little bit more work and a little bit more understanding of our models to understand what other composition or what other composite we're seeing in the spectrum. And so if you observe an exoplanet for the entire orbit this time, so not only when the planet is transiting in front of the star, you also get a phase curve. And so what you get from a phase curve when the planet is not necessarily in front of the star is, instead of seeing the light from the star passing through the atmosphere of the planet, you get the emission spectrum of the atmosphere of the planet. So you see light from the star, but you also see light from the planet, like I showed earlier. And so here, what I'm showing you is not JWST results, but rather this is a result with the Hubble Space Telescope. So like I said, JWST might be the predecessor of Spitzer because of the same infrared wavelengths, but it's also the predecessor, not a predecessor, the successor of Hubble, because we can do sort of the same science, almost the same science with the two of them for planets. So this here is a spectroscopic phase curve of WASP 141b with Hubble. And so you can see here, when you combine all of the wavelengths together, this is the phase curve that you get. And so this gives you some constraint on what the thermal map of the planet is. But what's really interesting is you can get a spectrum of what we call the day side and the night side of the planet. So a spectrum when the planet is passing in front and when the planet is passing behind, or rather the inverse. And then what you see is that on the day side of the planet, where the planet is being blasted with stellar radiation, so that means the atmosphere of the planet is really, really hot, we were able to detect water in emission. And so the planet, or the atmosphere of the planet in the day side was hot enough that it was emitting water emission features. However, on the night side, where the planet is cool enough, basically we were able to see water in absorption. And so basically, this is telling you about the thermal structure, or the difference in the thermal structure of the day side and the night side. And that can sort of help you understanding how this like global model of the atmosphere of the planet is. And so like I talked about Hubble, but the reason why I'm talking about Hubble here is that JWST is going to be able to do very much the same thing that Hubble did in better precision, but different wavelength. And so it has access to different molecules and different absorption feature that Hubble would not have been able to see, or would not have had the precision enough to be able to see. And one of these targets that Hubble had a lot of a hard time to observe are these lava planets again, that I talked about earlier. And so again, these lava planets are super exciting because they're super asymmetric, but they're also very extreme worlds. But with Spitzer, we were able to observe a tiny, tiny bit of the light from these worlds. But the truth is there are so many unknowns that we don't know about these worlds. And so we don't know whether these planets have sort of only an atmosphere that is covering the day side of the planet. So basically the atmosphere of the planet would be evaporated from the magma ocean. And then as you're moving away or far away enough from the substellar point of the planet, then it would get cold enough. And once it gets cold enough, you can have the entire atmosphere of the planet rain out and condense out. And on the night side of the planet, you wouldn't have any atmosphere. So this is not the first time that we're hearing of these type of atmosphere, but it's the first time that we're hearing about them outside of the solar system. And the reason why I'm talking about them is that they are particular favorite targets of the first cycle of JWST. So in the first year of JWST, you're going to hear about these lava planets a little bit more because we have a couple of data for a couple of systems coming down. One of them is 55 Cancri E, like I showed earlier, that we observed with Spitzer. Another one is GJ367b. I don't expect you to remember all of these names because they are complicated, or not complicated, they're not intuitive. And finally, there's also my favorite K2-141b, which is another lava world that will be observed with JWST, which I am involved in, and this is why I'm pretty jazzed about it. But now I want to come towards an end of this discussion about observing the climates of other worlds. So just to summarize, we talked about how to detect them. I talked a little bit about some of the discoveries and detections that were made with the Spitzer Space Telescope. And also, hopefully I got you excited for what's coming up next with JWST. But just to finish with a final thought, this is the very first time that I give a talk where I get to talk about JWST science as an ongoing thing rather than something of the future. So as you can tell, I'm particularly jazzed about this mission, which is projected now to have another 20 years of science. So basically, one of the unknowns when it launched is that we didn't know how much fuel we would have for the rest of the mission, because if we needed to correct the trajectory of the mission of the telescope as it was going, we would lose fuel. But it turns out that the engineers were super precise with the launch. And so we now have enough fuel for 20 years of science. And so I will leave you with the following tweet that I like a lot, which is a good summary of my PhD journey. So I just did a ton of research on exoplanets, and y'all, we know so much more than we did 20 years ago, but also we know nothing. But very soon we might learn something. And now I'm hoping that this leaves you with the conclusion that now is a really good time to be an astronomer. So with that, I will open the floor for a question.
So thank you, Lisa, for that wonderful presentation on exoplanets. Just before we move on to the Q&A, please make sure to register for our next session of the Physics Hour that will be next week with Patrick Desrosiers. It will be in French. It will be sur la complexité, la simplicité des réseaux de neurones. We will now